Well, aloha everyone. Today we're going to talk about Newton's laws of motion.
You've probably heard of Newton's first law before. An object in motion will stay in motion until acted upon by an outside force, and an object at rest will stay at rest until acted upon by an outside force. So, for instance, this little cart right here is currently at rest. If I don't touch it, and if nobody touches it, how long is it going to stay there? Well, a really long time, until something causes it to move. Maybe it gets hit by a meteor. Maybe the building falls down and it starts moving then. Gravity causes it to move eventually. But for now, as long as nobody's touching it, it's going to stay at rest, basically forever. If I take this thing and I give it a little push, it is now in motion. And you can see it stays in motion at about the same speed until it hits this thing over here. Yes, eventually friction is able to bring it to a stop, but objects in motion are going to stay in motion until acted upon by an external force.
So Newton's first law of motion is going to say something to the effect of objects in motion stay in motion, objects at rest will stay at rest until they're acted upon by an outside force. What do we mean by this word here? Force. Well, it turns out that that is a very specific meaning. It's just a push or a pull. So when you push on something or you pull on something, you are exerting a force on it. Now, force is going to be a vector, which means it has a direction. So if you push on something, you are pushing on it in a specific direction. We need to take that into account when we're dealing with forces. If it's on one-dimensional, you could say that maybe this way is positive. That means if you take something and you push on it that way, this would be a positive force. Whereas if you pull on it back this way, this force would be negative. If you have multiple dimensions, let's say there's a force going this way and a force going that way, what you're going to have to do is you're going to have to separate them into x and y components using the trigonometric functions. And then you're going to have to add or subtract corresponding components to see what that net force is, the total of all the forces. So when we say net force, we mean the total of all forces. And remember, we just don't add them. We have to take direction into account. So make sure you take direction into account. All right, so Newton's second law is actually a very important reference. Newton's second law you probably haven't heard before, you might have, but it's very rarely stated as a statement because it works much better as a formula. And that formula is going to be this: F net. The net force on an object, it's a vector. Or sometimes we're going to write it this way: sigma F. Which means, and F is a vector again, this sigma means the sum of. Means just add up all the forces. Take all those forces, put them together. Some will add, some will partially cancel probably, but you need to put all those forces together. This is equal to the mass times the acceleration. And the acceleration is a vector as well. So sigma F equals m times a, or the net force is equal to m times a. That means when you put a force on an object, it is going to accelerate. And its acceleration will depend on the force and how much mass that object has. If it has more mass, it will accelerate less. The second part of that is that the acceleration will always be in the direction of the net force, or the total force acting on an object. So if you had an object here, and you put a force on it this way, and you put a force on it this way, so force, force, the net force is going to end up being something like this. And so if you have two forces pushing on it like that, it's going to accelerate in that direction. Let's see a simple calculation with this. Let's say that we only have one force that is not canceling acting on an object. So this object is way out in outer space, really far from every planet and star and other object. So that therefore the gravity acting on it is basically zero. They're so small that we can't measure it, perhaps. And let's say we're over here and we decide we're going to push on it. Maybe this is an astronaut. So here's his spacesuit. And maybe he's going to push on this, and he's going to put a force this way. F is equal to, I don't know, let's make it 10 newtons. Oh yeah, by the way, the units for force are going to be newtons. And they're not actually newtons. The real units for this are kilogram meters per second per second. The reason we use the word newtons is because physicists get tired of saying kilogram meters per second every single time. And so we substitute that with an N. We give it a nickname. But we need to be careful, and we need to understand that when we write Newton, the unit Newton, we're actually talking about the unit kilogram meters per second per second. So let's say our force is 10 newtons that way. Let's say this box has a mass. The mass of this box is going to be 15 kilograms. And we want to know what is the acceleration of this box. What is the acceleration of the box? Well, if we want to know the acceleration of the box, we're just going to say F, sigma F I guess it is equal to m times a. I'm going to solve this for a, so I'm going to divide by m. So sigma F divided by m is equal to a. That's equal to the net force. Well, there's only one force acting here. That's 10 newtons. Divided by the mass is 15 kilograms. This is equal to, let's see, 10 over 15. I think that's 2/3, right? So 2 over 3 newtons per kilogram. Or maybe we will say 0.666 repeating. And remember, a newton is a kilogram meter per second per second. So kilogram here cancels kilogram there. And we're left with meters per second per second. And that will be the acceleration of the object. You can see as the mass increases, the acceleration will decrease. So if we make this box bigger, more massive, if we give it more stuff inside it, the acceleration that this box will have will become less and less. Now that brings us to another important point. And that's one of the things that is Americans have a very hard time understanding because we don't really have great units for this. But there's an important difference between what we call mass and what we call weight. So, mass, if you remember, you probably remember this from chemistry, maybe your 8th grade science. Mass is about how much matter an object contains. Whereas weight is going to be about the force of gravity on an object. So, weight is going to be a force. If I ask you what is the weight of something, weight is going to be a force. Force is measured in newtons. So this is in newtons. In the U.S. imperial system, we use pounds. Up here, mass is going to be measured in kilograms. In the U.S. imperial system, we use slugs. But you probably have never heard of that. Okay, so We're going to use kilograms and newtons in physics because we use metric measurements. And so if you are told that an object has, I don't know, let's say the mass of an object is, I don't know, how about 25 kilograms? Let's make it 20 kilograms. How about that? If the mass of an object is 20 kilograms, and what is its weight? If you're asked a question like that, so we have some sort of object here, and this object has a mass of 20 kilograms, and they're asking, what is its weight? Well, the way that we solve that, the way we figure that out, is going to be to figure out what is the force of gravity on this object. Now, we're going to assume it's on Earth. Unless otherwise told, it doesn't tell us anything about it, so we can assume this object is on Earth. If this object is on Earth, then we are going to have a very simple thing. The force due to gravity on the object is equal to a mass times the acceleration due to gravity. And actually, usually we don't use just a g there. We just turn that into a g, little g, to mean the acceleration due to gravity. This is equal to 20 kilograms times 9.81 meters per second. The force due to gravity is equal to, let's see, I think it's 196.2 newtons. So that's how you find the force of gravity on any object. Granted, if you're not on Earth, this g will change. So you need to be careful of that. If they ask you how much something weighs on the moon, or on Mars, or on Jupiter, you need to know what the acceleration due to gravity is for those planets, or moons, or asteroids, or whatever place you are.
So Newton's third law says, for every action, there is an equal and opposite reaction. So that means when you put a force on something, that something puts a force on you just as hard in the opposite direction. So, take for example here, we're pretty used to seeing these little carts here, but there is a kind of a cool feature on them. There's this little pin right here, and if I push it, this little plunger pops out. It's spring-loaded. So it does that sort of thing. So I'm going to put this right here, and we can see, boom, if I do that, it shoots out and across the track. So what was the action? The action was this plunger pushed that way on this end stop. The reaction was the end stop put a force on the cart that way, which caused it to accelerate in that direction, and it went flying across this way. It's a little bit easier to see if you have two objects that are about the same mass. So if I do this, put these together like so, what do you think is going to happen? They fly apart at about the same speed. However, as mass changes, that changes the acceleration of the object. So I'm going to make one of these masses quite a bit heavier. So this cart is now quite a bit more massive than this cart. If we try the same experiment, watch what happens. We can see this one goes flying off, and that one only goes pretty slowly. That's because even though there's the same amount of force, this one's pushing that one that way, this one's pushing that one that way, even though they're the same amount of force, their masses are different, which means their acceleration is different.
So that's really all there is to it, to Newton's three laws, at least the basics of it. We're going to see a lot of applications and a lot of different ways to use these laws, but those are the basics of the three laws. So, mahalo for watching, and see you next time.